Okay guys, so in this video we'll finally start modeling the COVID-19 epidemic spreading in a city. And before we begin, let me first introduce you to the basic mathematics behind how the virus actually spreads. And for that I have created a new Jupyter Notebook for you where we're going to build a model. And we're going to use a compartmental epidemiological model, okay? These models are called compartmental because they divide the general population into different compartments. And the particular model which we are going to use in this course is called SEIR, dividing the population into 4 groups. These 4 groups are the following. Okay, so in the beginning, when essentially nobody has been infected yet, everybody, the entire population is in the susceptible group. But once the virus is somehow introduced in the population, it can be a city or a country or another geographical area, then those first infected individuals move to the exposed group. Okay, and those people that find themselves in this group, they have already contracted the virus, but they're not infectious yet. Okay, it's called an incubation period during which they have contracted the virus but are not infecting others. After which those people are moving into the infectious group where they are already very dangerous. They are spreading the virus around and infecting others. Okay. And after the infectious period, the people in this infectious group move to the recovered group, which contains both those that recover from the illness, but also those that die. Okay, so it contains both the recovered ones and the dead ones. And if you actually go to the compartmental epidemiological model Wikipedia page, and there is a short description of how these models actually work. You can also check out the particular scientific papers these models are based on. You can see that there is millions of types of epidemiological compartmental models, and the simplest one being the SEIR one, which divides the population into just 3 groups. And there is tons of other models, as you can see here in the schemes. But the point being that all of these models, as you can see exemplified by these equations, they don't take into account the human flows. And this is something our course is essentially based on, because I'm going to teach you how to incorporate human flows into the spreading of the epidemic and how to analyze and visualize it. And the point being that it is very important to take this into account, because the virus essentially spreads the same way as people move. So if you want to understand how the virus will spread, you will have to incorporate the particular human mobility patterns into your analysis. Whereas these models have a basic assumption, a wrong assumption essentially, that there are no human mobility patterns, in the sense that they consider a uniform distribution of the population in a geographical area, and they assume that each person will pass the virus to the same number of people. Okay, which is absolutely not true, right? Because there are areas that are more densely populated and there are more people flowing into that area. So if you remember, for example, in the Yerevan population density plot, there was this central area with lots of people living there. So it will be just enough that the virus gets into that area, and then it will spread even faster to other areas, because there is so much connection, so many connections to that particular central area. That said, I gave you an introduction to why you see these parts in the equations, whereas you don't see them over here. By the way, this is essentially the same equation written in a in a differential equation form with the derivative form, whereas I have done it in a discrete manner to make it simpler. And I suggest we move to the equations and understand how they work.